I'd like to welcome the next few speakers. It's Amrita and Rashi. They have a combined experience for more than 10 years in IT security, and they're going to talk about invisibility and how to handle that. I'd like to give a warm welcome to Rashi and Amrita.
Hello everyone. Thank you for coming for the talk today. I'm Amrita. I work as a test analyst. I'm being paid for testing into software, or rather breaking into softwares. But here we are not came for breaking into anything. We are here to secure softwares. So I have overall 7 to 8 years of experience in this, and with me is my co-researcher, an old friend of mine, Rishikesh, who is also a security analyst, and he is into this field since last 4 to 5 years, and yes, this is all about us. And the topic that we'll be discussing here is like .11 veil, covert and camouflage, invisible Wi-Fi revealed. So whenever we see and open Wi-Fi in the airport, maybe in the coffee lounge, or maybe in McDonald's, what is our reaction? Yay, I got free Wi-Fi. So that was my reaction till yesterday. But then today morning when I woke up, as a habit, I reached out to my phone. You can say a phone addict. I went on to checking my emails, my WhatsApp messages, my other accounts. So the thing that caught my attention was, in my WhatsApp account there were 2 messages, or say messages from 2 accounts. I have received few messages in that account, but the messages were received when I was sleeping. So I haven't actually read that, but the status shown was read for that messages. So that caught my attention. I was a little confused because I was the only one in the room. So how is it possible that how that status is read? So I have dig deep into that. So I came to a conclusion like there are 2 possibilities that this can be done. Like one is like hacking into my GSM connectivity. Another thing might be hacking into my Wi-Fi connectivity. All we know is, like, for hacking into GSM connectivities, we need few devices, few privileged devices that we are not allowed to carry everywhere. So that was a less possibility, and by selection, by elimination process, I came to an option, which was the only option actually, that my Wi-Fi connectivity is compromised. So then I dig more deeper into that. Like, I tried to find out that to which access point my device is speaking to, thanks to aircraft engine. So I found that to which MAC address my device is speaking has no SSID actually. So that created more suspicion. I tried to find out in that periphery which other devices are speaking to that MAC address. So I found that the other devices that are speaking to that MAC address, I mean, it has same MAC address, but okay, now this is working good. So that MAC address has SSID. So that leads to a conclusion that, or maybe more confusion, that there was a MAC address, same MAC address. There was no SSID to my device. There was an SSID for the MAC address that other devices are approaching. So I have been attacked? Yes. So that was my conclusion. And this is the current state of Wi-Fi, open Wi-Fi nowadays. So we are here to propose an approach, to propose few approaches that would reveal the covert communication that I actually experienced today. So let's get into some technical details of this. So our today's agenda is introduction and some details that I have already given, covert communication, the approaches that we are presenting, L2 in this approach, we are actually doing some data trafficking into some frames where we are actually sending on to some data which are where we do not actually expect that data will be sitting. As we all know, data is sitting in the payloads, but there are other ways from where we can send data. The next approach will be the patch peloton approach. We'll be using driver patching here. There are many things that we have learned during this experience and during this excursion, I would say. And we are still learning, and we will be still working on some potential approaches. There are few other approaches as well, but they are not yet qualified to be presented, and there are conclusions and acknowledgements that we'll go through. So this is all cluttered, right? So I mean, people here, this might be like Latin, Greek, or I mean, you might not be able to stand this, or I mean, this was our phase as well, a couple of years back when we started this excursion, and but later on we got some clues, we got things sorted out, things were falling in place, and then we were able to say, yes, we got the way out. So now we are like sorted. So slide itself says that. So what we say is, yes, don't trust payloads, but trust beacons. So we'll be doing the data trafficking using some of the frames in beacons. So yes, we'll be discussing deep into that. The story behind all of this is like there are few untold pieces in the book that is IEEE 802.11, which is a good book, great book. It's like 6,000 pages book. We might have read it. So, but they haven't disclosed everything in that. They have just suggested a very legitimate way to use their standards, and in a very what I would say, in a very quality manner. But wittingly or unwittingly, they have prevented disclosing few things. They have prevented disclosing few fields like parameters, fields. So that can be otherwise used for data trafficking. And yes, so is the Holy.11 wireless 802.11. So the character of these stories are less access points. Access points are used as a trans receiver, and they can be connected to multiple hosts for sending out the data and for receiving the data. And host can connect to the access point, can talk to access point, and from there talk to the internet, and then by that talk to the world. So we need to go deeper. This is not sufficient, I know. So let's see. Back to some of the basics. We'll do some introduction and prologue here. So .11 Wi-Fi, open Wi-Fi's are very famous. As I said, my reaction was like yay when I found open Wi-Fi. But then again, open Wi-Fi's are more prone to attacks, more vulnerable, and yes, they are like more buggy nowadays. So do we need a proof to call bug a bug? Maybe, may not be. Let's see. So there is a hole in the network perimeter, open wireless networks, WEP, I mean, this is cracked since 2002, and right now we need a couple of minutes to just broke into this. And now most of the industries don't use this, so this is like a past. Pat configs, configurations like admin password. So this led to a more vulnerable networks. Loose link in client security, offensive rogue access points, eavesdropping in socially dense areas, and connectivity mess-ups. So yes, these are also more vulnerable things. There are many victims adding to my device. These are a few more victims like mobile phones, cameras, printers, gaming consoles, laptops, desktops, or through whichever medium we can connect to internet and send the data. And like okay, so right now in today, like ICS, that is also more prone to be a victim. All in all, many victims awaiting exploitation. There are few .11 modes that can be used. First mode is like managed. Managed mode is where your interface card acts as a station. Ad hoc is also a form of managed mode where station can be used ad hocly, and that is why it's called as ad hoc station. Master mode, there are few revelations in this case that will come back to this point later on. This mode. Monitor mode, it shows everything seen by the radio. And yes, so this is me, and for more details I will hand over the communication to Rishikesh. He'll guide you through.
Thank you, Amrita. Well, yes, covert communication. These set of characters are pretty juicy information that everybody would love to see in their career of information security, I would say. So let's dig deep into that. So by book, what actually covert communication is? In computer security, a covert channel is a type of computer security attack that creates a capability to transfer information objects between processes that are not supposed to be allowed to communicate by the computer security policy. Making it more simple, there are always some ways to smuggle data onto any network channel, we can say. As of now, our case study basically deals with channels which are pertaining to wireless. So there are always been ways to smuggle data using various layers in ISO-OSI model. In this particular talk, we'll be dealing more with data link layer. Yeah, I mean, if we consider application layer, there are again different types of bridges we can implement in order to reach or rather in order to achieve covertness as far as communication is concerned. So we have been focusing on some of the aspects in data link layer, and that too specifically on beacons and probes. So let's learn why specifically beacons and probes. Before that, allow me giving me some introductory understanding on .11 frames, like wireless frames and their types. So there are basically management frames, control frames, and data frames. So management frames, I have just enlisted few of them here, like association request and response, reassociation request and response, probe request and response, beacon frames, so on and so forth. There are actually plethora of such frames here, but as of now, our interest, or rather the thing that we tried experimented, was upon probe request and response and beacons. Going further, this is just a formality, as we have mentioned, like management, control, and data frame. I just am enumerating them here. So it is like control frames, RTS stands for request to send, CTS stands for clear to send, ACK, PS poll, so on and so forth. In case of data, it is AMSDU, different variants of MPDU. As of now, this is not of our concern. So let's go to the first approach that we have proposed to achieve, or rather to smuggle data over a legitimate wireless channel. The name of that approach we have put here it as ELT euphoria. ELT is actually, we have borrowed this term from SCAPI terminology, where we use a particular field or rather particular construct called .11 ELT. So that actually infers to information element. So ELT is nothing but information element, part of wireless frames. Beacon frame is essential element in the wireless networks. Yes. Beacon frame populates here with a rate of around 1 frame per 100 milliseconds. So around per minute we receive 600 beacon frames. So as we see the number, it is abundantly available into local radio periphery. So they are broadcast, yeah, that is advantageous for us. And they do not require any authentication or association with access point to listen to them. So some very basic structure of beacon frame we see here. There are various parameters we can see. Out of that, as of now, we will be focusing more onto this parameter called TIM, stands for traffic indication map. We'll come to that soon. So some small animation. I know the graphics are pretty blurred. I have borrowed it from Wikipedia. So this actually tells like how access point is advertised in beacon frame. So whensoever a beacon frame is injected into the local periphery, what it does, it actually is a broadcast. So for receiver address, it's going to be all F fields, and there would be an SSID which would be embedded into beacon frame. So that is all the information that all of us know about beacon frame, right? But there are certain parameters as well which can be used in order to traffic data. So there's a lot of information stuffed inside wireless frames in our context, beacon frame or probe request and response. Yeah, before we go further, let me tell you what is a probe request and response. Suppose today here we are sitting and there is a network called BruCON, a wireless network with an SSID BruCON. So here we have connected to that device. So in some cache of our phone or maybe of our laptop, this particular SSID is saved. So tomorrow if I go to maybe another hotel, let's call it as a Novotel, and there I just start my device, or rather I enable my wireless feature of device, the initial set of injections that my wireless set of device will do is like it will send certain frames just to see, like in past I was connected to BruCON as a network called BruCON. So is that network available into this present local radio periphery? To check that, it will inject certain frames. So these injected frames are nothing but probe requests. And if these requests receive certain legitimate response, then that is called as a probe response. The difference between beacon frame and probe request response frame as far as format is concerned, it's only a couple of fields are changed, or rather the numbers are changed. In case of beacon frame, the subtype is 0x08. In case of probe request, it is 0x04. So that is only the difference. So yes, I think that's elaborate about probe request and response. So how to harness the true power of these frames and aid the fields which have better lengths in order to ship data. So going further, like let's come to the point what exactly information elements have to do with our talk. Information elements are certain piece of information as far as hardware, some power rating, some different properties of that particular wireless network interface card is concerned into that context. So interesting elements like this particular information element has got 256 different variants. According to the IEEE 802.11 draft that's been released in 2012, there are 256 possibilities of information element. Out of them, as of now, there are around 121 information elements are in practice. Out of them, we have picked a couple of them for our experimentation. So Some of the interesting elements we have listed here as SSID stands for Service Set Identifier. Then DS set, kind of again some parameters we use, and TIM stands for Traffic Indication Map. Rates, again different parameter in case of information element. ES rates, TPC requests and response. Recently we found some juicy about this as well. And country, yes. Again, this particular element has got some capability to ship data over legitimate channel. So why particularly beacon or probe frames? As I've said earlier, these frames, they do not require authentication or association to air themselves. Being broadcast, so no need to zero down on host selection. Like, we need not pinpoint to a particular host in order to run an attack. Had it been a multicast or a unicast, that would have been a test case we have to take in consideration. So it's like we just bursting out, it's like fire at will. Presence of these frames in multitude in local wireless periphery is a common phenomenon, hence escapes suspicious eyes initially. What I mean to say here is like there would be some filtering devices, there would be some monitoring devices. So instead of 600, there might be some 6,000 beacon frames present per second. But no suspicious activity would be logged in case of filtering devices or in case of your UTMs for that matter. Again, the multitude will always facilitate the larger chunk of data to ship. Yes. Outbreak of malware? Yes, always a possibility. Some fields allows pushing more than 250 bytes of data in a single frame. So now, many of you might be working for some threat intel company or maybe for some exploitation, maybe in an exploitation business. So they know very well importance of having 250 bytes in a single chunk. What all can be done using that. So they are pretty much enough to ship a malicious payload. So yes, I have here just tried to mention what field we'll be taking into consideration, that is TIM, Traffic Indication Map. So why particularly TIM? If we break down TIM into pieces again, we will see that there is a particular field called Partial Virtual Bitmap. This is the field which allows you ship data between 1 to 251 bytes, which otherwise is used to ship certain buffered data when your network interface card is in a sleep mode. So TIM allows shipping data of around 250 bytes in a partial virtual bitmap field. Essentially, it was easy to fabricate the frame in SCAPI with this information element. So I just have prepared one probe request. Why probe request? It was basically because while actually crafting a beacon frame in a SCAPI, that frame was getting prepared on my machine, was getting interpreted in my kernel, but it was not escaping my machine. Somehow I was unable to broadcast that particular beacon. So is the reason I have taken in account probe request and experimented same thing. If we see here, this partial virtual bitmap shows a huge string, right, which otherwise is not crafted automatically using your drivers or maybe using your operating systems. And if we see the translation of that particular string, here we can see it is some meaningful text. So I have actually tried write some script for this, which was very well working for with my earlier box. This is a new box. I am unable to work that out, but still I'll share that thing with you. I'm sorry. So this was the raw SCAPI script I tried, right? So I have actually imported everything from SCAPI in order to run it in a Python environment. I put some source MAC address, that is my network interface card's MAC address, then destination MAC address. Yeah, I kept it purposely broadcast because it is a probe request. So it has to be reached every network interface card or every intelligent wireless network device present into the local radio periphery. Then SSID, I have crafted certain parameters here for SSID, that is .11 ELT, then ID is SSID, and information, this is nothing but the name of SSID, I put as all A's there. So for traffic indication map, I have again prepared another construct, and that is like very well available with our SCAPI. So here we have put an ID as a TIM, that is nothing but the name of information element. Then info, I have just put it as a BruCON all the way. And then I have just layered these particular constructs over each other in order to build a packet or a frame. So if you see here, this is the frame I tried build. And when I tried run this, as of now, it was giving me some encoding error. It was just 5 minutes back I have come across that error, so I could not rectify it. But earlier, with some certain tweaks, maybe if we spend an hour or so, we can make it run properly in order to ship this particular data. So as of now, I'm using certain bytes of 250 bytes. Now what if I put actually a raw shellcode here and send it over? Well, there would be requiring some work around for that, like how this particular raw shellcode will be interpreted by victim, like where actually it will be landing, or maybe we need to find particular vulnerability in a wireless driver for that matter, or maybe some kernel interpreter, or maybe kernel object for that matter, where this can run and can produce some good output, or maybe a shell. So this is what we've been trying to achieve, but this thing is workable. We have made it work, so is the reason we can see this screen capture. So the issues with this approach, so if somebody is doing a deep packet inspection using firewalls, then there will be a suspicious alarm generated for this, because we are shipping a lot of data into some element which otherwise is not supposed to send such a huge chunk of data. Reordering the data at receiver end could be an issue should sequencing is not taken care of before showing in the data. As I have told, like yes, 250 bytes we can send very well, but if my data size is beyond 250 bytes, then yes, there are certain issues we still are working on how to sequence that data. There are certain parameters like timing and ID parameters which can help us doing that. But so far the output is unstable. I'm receiving some garbles in some cases, in some cases we are receiving proper output. So as that is not tested perfectly on all grounds, I haven't produced the output here. No retrieval of lost frames so far. So as we are still struggling with this whole sequencing issue, we could not actually work upon retrieval of lost frames as well. And as I have told already, like SCAPI doesn't support beacon injections swiftly. That is still an issue. For that, the workaround is like we're supposed to write a simple C program in order to generate that particular beacon frame and wrap that over into Python environment and send it over. So maybe C types will help, but me being not very core programmer, I still am struggling with this. Yes, so having considered these particular issues or drawbacks of this particular approach, we have worked around this and found something else. So minute divergent to Altioforia, where we have considered some different type of frames. Like in case of control frames, we've been talking about clear to send and request to send. These frames are actually succeeded by a frame called ACK frame. So now the thing here is like whenever we consider an acknowledgement, a host, before we go further, this type of attack is going to be majoritarily either unicast or multicast. Just because acknowledgement is supposed to be sent for a particular communication which has already been initiated, so this will not actually help in case of broadcasting attacks, we can say. So ACK frames or response frames are of significance to reply to certain communication initiated by the remote host earlier. So we are in some comfort zone. We know like, yes, there is some communication initiated, there is already some information exchange happened. So now can we write certain data over these ACK frames or response frames? So the trust is already in place between two hosts. The responses or acknowledgements sent by unsolicited user will receive little low priority of inspection as it has assumed that such responses are bound to come from a legit source on peripheral devices. Adding this approach with the elder euphoria will give solution to the sequencing issue. Why? It is just because already there is some set of activity done. So to have this particular activity completed, there is some sequencing mechanism already in place. So we need not reinvent the wheel or rewrite that whole logic in order to generate that sequencing mechanism here. The response traffic is always made more intelligent as they are capable of assigning sequence, discipline the traffic at receiver end, as I have just explained you. The parameters which could come handy are frame control sequence, more data, more fragments, sequence numbers, BSS ID, ESS ID, and essentially source address. So what actually we did into this is like, we have encoded the data and shipped it over an ACK response, we can say. Before doing that, how did we encode the data? We have used certain logic. In that logic, we have embedded and pre-shared with the user in the parameter called ID. Sorry, we have used the ID parameter to encode the thing, and then we have shipped this thing over. This secret was already pre-shared with other party. And then we have run this partial stealth mode on legit acknowledgement. This may actually lead to some ad hoc network scenario where we are actually tweaking into protocol stack, we are changing certain things. So this may not always abide by the rule sets which are produced into IEEE 802.11 standards. There might be some diversion, and yes, we did that diversion as well. So resulting in more autonomy and more control over the data. Yes, that is possible just because we are altering almost everything that is needful to make our conduit or rather covert conduit legitimate. So the issues, yes, we still will be facing issues from anomaly detection based firewalls, you can say. The loss frames are still an issue. Yeah, in case of sequencing, we can achieve certain success here, but as far as loss frames are concerned, there is actually no clue that there is some frame which been sent from host A to host B. So how to make it resend? So host B have no mechanism to gather this intelligence. Hence, host B cannot actually tell host A, yeah, I'm triggering this alert because I did not receive this frame. So this thing is still missing. So these were two approaches. We are still working upon them. There are certain more fields we have been considering, and yeah, outputs are little varying, so is the thing. So the third approach is a little different. Here we are not crafting a packet or frame. In fact, what we are trying to, we are doing that, but that is in a later stage. Initially, what we're trying to do here is we are trying to patch the network drivers. So what we found here is like the driver patching is one of the most efficient way of achieving invisibility in the air. This approach fairly mitigates the issues we have confronted in the previous approaches. Having this said, it is truly covert conduit setup for securing the communication over the air. Before we proceed further, this patch peloton approach is actually inspired by the work of Dr. Lauren Butty. He is a researcher in 2006, Black Hat DC. He have actually produced research on same covert channel and covert communication. He have used driver patching itself, but the parameters he have used for driver patching were different. And the parameters that we are using for driver patching here are different. So truly speaking, he deserves the credit. So I just am having his mention in this talk because he's my inspiration basically in this. So the test case, we have devised certain test case for this. So what we have done, we have prepared two hosts. So one host is having, these two hosts having patched drivers. We have used Unix machines as of now because these things were more swifter on Unix machines, having known the kernel code and things like that. Windows machines also we have used just in order to check whether whatever the covert traffic that we're trying to do using these patched drivers, whether that is detectable on some unpatched machines as well or what. So for scanning and stumbling purpose, as we've seen. So what we've done is like we have raised an access point on one Linux machine by tuning into master mode with having the patched drivers enabled on it. The machines with unpatched drivers will not be able to see the engineered traffic. The machines with patched drivers will be able to communicate with their devices having some patched protocol stack, having same protocol stack. So what were the deductions? Before we go further into further detail into this, what we actually tried to patch here was like for a legitimate wireless frame, let's say version field, we consider it as a 0 always. Like analogously in case of IP packet, if we say like it's an IP packet, there are two variants of version field we consider it is either 4 or 6. Parallelly, same time, if we consider wireless frame, version field into the wireless frame so far is kept 0. Here in this patch, what we've tried to do is like we have changed that 0 to 10. Hence, whatever the data that we have shipped having our frame crafted with version field as 10 will otherwise will be dropped by those all hosts which are not actually having a patched driver. But in case of a patched driver, this particular frame will be interpreted by kernel and will be fed further to the appropriate process. So the deductions from this approach are: engineered beacon frames from access points with patched protocol stack were not read by the devices having unpatched protocol stack. Neither of probes injected by devices with patched protocol stacks were read by the devices with unpatched version of protocol stacks. Sniffers gave little variation in the dump of traffic. Yeah, we have received sometimes some garbled text. Sometimes we have experienced a lot of we have experienced a lot of crash as well. We are still facing that thing. Actually, as right now we are running majority of Linux machines onto kernel 4.x. So this experimentation was basically done on kernel 2.6 onto my desktop box. But post that whole implementation is failing somehow. So I could not produce the output here. But yeah, this thing is pretty much workable, and we've tested it on some lab environment, we can say. So in some cases, devices with unpatched protocol stack were not able to sniff engineered traffic at all, and some dumps gave a garbled traffic. So yeah, so the results were mixed. So what was the advantage here? What are the set of advantages rather? In-house solution for mitigating majority of attacks on wireless infrastructure. Partial occurrence of event horizon in wireless networks is very much achievable using this approach. Yeah, because see, we are sending certain data which is only interpretable by certain kernels, or rather interpretable by certain drivers which are patched. So, suppose I say like I'm sending data from A to B and B to C, and if C is trying to trace back from where this data is originated, this whole trace is ending at B, because post B, whatever traffic that device is trying to do is not interpretable at all. So it will always receive certain ICMP responses from host B back to host C. So yeah, so that is one of the advantage we can say. This actually, if we successfully build a patch, this doesn't actually require a lot of edit. We just need to run that patch onto our driver and things will move smooth. So requires no great deal of changes in operating environments other than patched drivers. Low cost, low effort solution, we would say it. Yes, these things are so far working good on Linux boxes, not onto Windows. We are yet to test these things on Windows boxes. So what we have earned or learned in learning out of this is like there are many issues with SCAPI. Like we were big time relying upon SCAPI for injection purpose, for for various packet crafting purpose. But it's been found, like while building frames in layer 2, that is data link layer, Scapy gives many errors. At certain place it gives certain outputs which are like totally absurd, and that will actually land you in a lot of confusion. Building patches takes a lot of input from various sources. Yeah, in case of latest 4.x kernels, even it inherits certain resources from operating system as well. So it's not mere a driver we're supposed to patch. We need to take care of certain resources from operating system as well. So that is actually preventing us from compiling this whole thing properly into 4.x, you can say. Yeah, so that was all so far. So potential approaches, as I've told, like there are certain different requests and responses, certain fields into information elements we've come across, which are again capable of shipping some data. So recently we have identified that this TPC request and response are capable of shipping data more than 200 bytes again. We have tested TPC responses, but we could not somehow test TPC requests properly. Yesterday only I was able to find that country, the name of this particular information element ID is country. This again is capable of shipping 256 byte of data. So this can again be exploited in a proper way in order to send or rather smuggle the data over legit channels. So far, as I've told earlier as well, like we have explored only version field in the driver patching. There are many more fields. Yeah, there was a question like why specifically version field we have picked up. It was just because that was one of the constant field we have used into wireless frame. But apart from that, there are many other fields as well. Like there are certain fields which are lying around into power management, certain things into frame control sequence, that is FCS. So these fields also will actually help us coming up with some different type of covert channel. Yes, PS pole frame is also an interesting carrier, yet we could not work the traffic so far. Why PS pole frame? Because whenever we say like we are polling particular device, what we're trying to do is like we are actually inheriting certain buffered data and then shipping it over again. So what if instead I'm waiting for that device to wake up and send the data over as my polled data? I can very well alter that data to whatever my desired input is and can ship it over. So that was the motive behind doing this PS poll framework. So yeah, so conclusion. So wireless networks have a different way of securing as well by mean of running covert channel. The approaches we have proposed are still in development so far, which with the help of minute automation can lead to nicer outcomes. As I've told in case of euphoria, like what if in that particular traffic indication map, I put certain data and make it readable by my kernel. So then I'm capable of actually running kind of a bot onto various devices, and then just it's a matter of that agent handler mechanism or an algorithm in order to have them all operated in a proper way. Yes, the approaches we have proposed are still in development. Oh, I'm sorry, I'm repeating this. Acknowledgements. I have been following closely the literature given by Vivek Ramachandran. He has actually set up a course called Wireless Security Mega Primer. So basic understanding I have gained from his Mega Primer as far as the frames and packets are concerned. Josh Wright for his blog Will Hack for Sushi, helping a lot regarding Scapy scripts. And yes, BruCON 2015 for hosting such a nice event and allowing me to present, or rather allowing us to present over here. Thank you very much for your patience and listening to my talk. If you have any question, I'll be glad to answer them.